In this module, we are going to transition from empirical models to more mechanistic approaches to describing systems. We will start by looking at some simple systems and introduce you to some of the basic terminology we will use to describe systems in the process of modeling these systems. Upon completing this module, you should 1. Have a basic understanding of what constitutes a system, including the fundamental building blocks of stocks, flows, and influences. 2. You should be able to represent a conceptual model as a systems diagram, identifying these stocks, flows, influences, and a system boundary. And finally, you should be able to identify positive and negative feedbacks in a system and understand the consequences of these feedbacks on system behavior. So what is systems thinking? System thinking offers you a perspective, a language, and a set of tools that you can use to address complex problem solving. Systems thinking is a way of understanding reality that emphasizes the relationship among the system's parts rather than the parts themselves. And finally, systems thinking is based on a field of study known as systems dynamics. It has a practical value that rests on a solid theoretical foundation. For the next portion of this course, we will be exploring systems thinking through the lens of mathematical modeling. So let's define a system. We saw a few examples in the introduction to this course. Here's one we saw previously. This is a conceptual model of nutrient cycling in a wetland, highlighting important components such as nutrients, peat, and living biomass, as well as important processes like atmospheric deposition, mineralization, and losses to deep sediments. Here's another one we saw previously. The representation shown here is more abstract and conveys fairly precisely all of the relevant information in the system, including the stocks and flows. Also shown is the system's boundary, defining what is internal and what is external to the system. This is also a model of a wetland, but from a more of a whole system perspective, a different lens resulting in a different system conceptualization. These systems diagrams convey the connectivity of the system that has important consequences for system function. For the next portion of this course, we will be exploring systems through the lens of mathematical modeling. So, let's define a system. A system is defined as an interconnected set of elements, organized in a coherent way, that achieves some function or purpose. At the most basic level, a system consists of elements, which are sort of the nouns of a system that represent stocks of important things that we are tracking in the model. The interconnections, which are sort of the verbs in the system that represent processes that move material or energy from stock to stock or across system boundaries. And finally, there's information that flows in a system, the influences in the system that control and regulate the flows throughout the system. Can you think of any examples of a system? A better question might very well be, can you think of anything that is not a system? One more thing we'll note about systems. They are often more than the sum of their parts. They are often adaptive, dynamic, and difficult to understand. That's part of the reason systems are capable of doing work, whether that is a car driving down the road, a wetland cleaning water, or a watershed growing trees and sequestering carbon. To get started, let's look at a really simple system, a reservoir of water with upstream inflows and downstream outflows. We can represent this conceptually as a single pool or stock of water with two flows, one coming from upstream, one coming from downstream. We also show a system's boundary to indicate what is internal and what is external to the system. We treat the upstream flow as an external source and the downstream flow as an external sink. Our stock, water, is moving across the system boundary for both of these flows. We can do a mass balance around the stock that generates a differential equation describing the rate of change of the stock through time, as long as we know what the inflow and outflow rates are. Once these are specified, we will have a mathematical model of the dynamics of the system that will allow us to predict the level of water in the reservoir at any point in time, given some initial starting value. We will have to figure out how to integrate this equation to get a solution, and we'll discuss methods for doing so as we move throughout the class. Let's look at some basic but common systems. For example, consumption of a non-renewable resource, say a mineral deposit. In a systems diagram, consumption might look something like this. A single stock of minerals, a flow that removes minerals via a mining process, and a system boundary so we know what's inside and what's outside of our system. As before, we can do a mass balance to mathematically describe this system. Calculating the rate of change of the mineral deposit based on the rate of mining, and nothing else in this case, is what this differential equation depicts. Note the negative sign on the mining term. This indicates the process of removing chemicals from the mineral deposit stock. As before, integrating this equation will allow us to predict the stock of mineral deposits at any point in time, given an initial mineral level and the rate at which mining will occur. Also note that, although we are describing mineral extraction, the conceptual model is valid for any consumptive process. The details will vary with the process being captured, but the general approach remains the same. Here's a slightly more complicated version of the reservoir model we just saw. This one has explicit flows for precipitation, upstream flows coming into the water reservoir, and losses due to evaporation off the reservoir surface and downstream discharge. A mass balance provides our model once we specify the four rates indicated on the right-hand side of the differential equation. Note that the inflows have positive signs, indicating they are contributing to the stock. Outflows have negative signs, indicating that they are removing from the stock. Further note that a stock can be increased by either increasing the inflow or decreasing the outflow. Here's a systems model of a small woodlot producing timber for lumber sales. In this system, we have two stocks of interest: the wood in the living forest stored as live trees, and the harvest wood that has been milled into lumber for sales. The model captures important processes in this system, including tree growth contributing to the stock of living trees, with losses from logging and tree mortality, as well as processes affecting the lumber inventory, including inputs from logging and losses due to lumber sales. Because we have two stocks, or state variables, in our system, we will have two coupled differential equations to solve, both capturing the mass balance of inflows and outflows. Again, we will need initial conditions and the details on the four processes in the system to solve these equations through time, as well as an integration method that can handle coupled differential equations. We also note that stocks generally change slowly relative to flows. They act as delays or buffers in a system. An aspect of systems we haven't defined yet is information, and an associated topic, feedbacks. Information feedbacks are essential for controlling and maintaining systems of all types. To quote J. Forrester, an early systems scientist, systems information feedback control are fundamental to all life and human endeavor, from the slow pace of biological evolution to the launching of the latest space satellite. Everything we do as individuals, as an industry, or as a society is done in the context of an information feedback system. Information typically propagates from stocks, what we'll call state variables, to flows to control the rate of the flow. Feedback loops form when stocks control, either directly or indirectly, an inflow to or an outflow from itself. These are important regulators of system behavior. Here's an example of an information flow in a systems diagram. The model is a stock, what we'll call population, experiencing growth, contributing new individuals into the population. Also depicted on the diagram are two influences, representing the flow of information in the system. One influence originates in a model parameter R, a per capita growth rate constant depicted with a circle on our systems diagram, and exerts control on the growth rate process. Another one originates with the population stock. It also exerts control on the growth rate. Our mass balance reveals that the population will grow continually as long as R, the per capita growth rate, is positive. Our influence manifests themselves in our rate equation as the R times P term on the right-hand side of the equation, capturing the concept that both R and P influence the growth rate. We note that the RP term, R times P, in the rate equation represents a feedback loop. The population is controlling the population's growth rate, which in turn is affecting the population level. The positive sign on the RP term is important. It indicates that this is a positive feedback, which we will refer to as a reinforcing or runaway feedback. This type of feedback is valuable because it tends to cause the systems to do useful work. Growing a forest, producing a product in a bioreactor, which is generally a good quality of a system. If we solve the rate equation by integrating it over time, we get a plot like the one shown. Given an initial condition of, say, 2 units of population and a per capita growth rate constant of 0.2 results in a solution to the rate equation that, perhaps as expected, increases as a result of growth, but the rate of growth increases as the population increases, with the feedback loop leading to runaway growth in the population. Ultimately, this system will fail because the growth rate tends to infinity, an unsustainable prospect. Here is a different example of information flow in a systems diagram. In this example, the model is of a stock that we've used before, population, this time experiencing a loss, mortality. Also depicted on the diagram are 2 influences representing the flow of information in the system. One influence originates in a model parameter K, a mortality rate constant depicted with a circle on our systems diagram, and exerts control on the mortality rate. Another one originates with the population stock. It also exerts control on the mortality stock. Our mass balance reveals a consumptive process for the population P. Our influences manifest themselves in our rate equation as the K times P term on the right-hand side of the differential equation, capturing the concept that both K and P influence the mortality rate. As in this last example, the system is controlled by a feedback loop, captured in the minus K times P term in the rate equation. The population is controlling the mortality rate, which in turn is affecting the population level. The negative sign on the KP term is important. It indicates that this is a negative feedback loop, which we will refer to as a balancing or stabilizing feedback. This type of feedback is valuable because it tends to balance or stabilize a system, making it resistant to change, which is again a generally good quality of a system. If we solve the rate equation by integrating it over time, we get a plot like the one shown. Given an initial condition of, say, 100 units of population and a mortality rate constant of 0.2 results in a solution to the rate equation that, perhaps as expected, decreases as a result of mortality, but the rate of mortality decreases as the population decreases, with the feedback loop stabilizing the decline in population. Ultimately, the system becomes very stable with a population of 0, perhaps a little too stable if we want this system to do work for us. For virtually all systems, system behavior is controlled by balancing positive and negative feedback loops. The positive feedbacks generally allow the system to do work. The negative feedbacks generally allow the system to stabilize and balance. Here's an example of a system with both positive and negative feedback loops. Our system examines the dynamics of algae growing in a bioreactor. Algal dynamics are controlled by a growth process contributing to the stock and a mortality process that is removing algal biomass from the system. The growth rate is controlled by a per capita growth constant, K, and a shading factor, SH, reflecting the shading effect on the ability of algae to grow, and the current stock of algal biomass. There are 2 feedback loops involved with the growth process. A direct influence of algal biomass on growth. The more algae, the faster the algae can grow, and an indirect influence via the effective shade term. The more algae shade other algae in the system, limiting their ability to grow. One of these is a positive loop, One of these is a negative loop. Which one is rich? Remember, positive feedback loops tend to speed up rates of change. Negative feedback loops tend to slow down rates of change. In this case, the direct feedback loop is positive and left unbalanced would cause runaway growth of algae. The indirect feedback loop via shading is a negative feedback loop, preventing the runaway growth and subsequent system crash. There is one more additional feedback loop in the system. Can you find it? It is related to the mortality process. As algal biomass increases, the mortality rate also increases, slowing down the growth of algae. Is this a positive or a negative feedback loop? It is a negative feedback loop because it tends to stabilize the system. Next, let's look at the mathematics of this system. We have a single state variable A representing algal biomass with terms in the rate equation for A for growth and mortality processes. Our shading factor is influenced by A and a model parameter A max as shown in the systems diagram. The A max parameter is the maximum density of algae before shading completely shuts down growth and is a constant in this model. The overall growth rate is determined by multiplying the per capita growth rate times the effective population, which is the current algal biomass level modified by the shading factor. Note that the growth term incorporates the positive feedback loop capturing exponential growth and a negative feedback loop capturing the effects of shading. Also note that in the differential equation dA dt, positive feedbacks show up as positive terms and negative feedbacks show up as a negative term. Some of the questions we might ask of this system include 1. What is the dynamic behavior of the system? And 2. What are the key interactions that control the system and how can we maximize the biomass generated by this system? So, to recap, in this module, we explored some concepts around systems and systems representation. First, we said that systems can be characterized by the stocks, flows, and influences that represent important components of the system. Stocks, otherwise known as state variables, represent quantities of mass or energy. Flows typically represent processes that transport stocks around the system, and influences represent information flows controlling system behaviors. A system's boundary determines what is in and what is external to a system. Second, systems diagrams can be a useful way to represent a system. Systems diagram can be useful tools for communicating a model representation, and they can also provide the basic mathematics used to characterize the system. Third, feedback loops are the way systems control themselves. They are information flows that can drive and stabilize system behavior. Positive feedback loops reinforce systems behavior and can lead to runaway system processes that in turn can lead to system failures. Negative feedback loops tend to stabilize and balance the system. Fourth, a well-designed system incorporates positive feedback loops to accomplish work and negative feedback loops to stabilize the system. Both types of feedbacks are necessary to maintain a functioning system. In the next module, we will look at some simple system models examining population dynamics and begin to explore techniques for solving these models.